Ever pondered how data packets find their way around the internet? It's thanks to routing protocols like OSPF. Indeed, the internet, this gigantic web of interconnected devices, is not as chaotic as it may seem. It operates on a set of rules and protocols, one of which is the OSPF, or Open Shortest Path First. OSPF, as its name suggests, is a routing protocol used within large and complex networks. Its primary function: to find the shortest and most efficient path for data packets to travel from one point to another on the internet. Now you might be wondering, why is it called open? Well, this is because OSPF is an open standard protocol, meaning it is publicly available and can be used by any vendor. This makes it a versatile choice for network engineers dealing with multi-vendor environments. And what about shortest path first? This part of the name points to the algorithm OSPF uses to decide the best route for your data packets. This algorithm, known as Dijkstra's algorithm, calculates the shortest path between nodes in a network. It's like a GPS for your data, except instead of avoiding traffic jams, it's navigating the data highways of the internet. But OSPF isn't just about finding the shortest path, it's also about finding the most efficient one. OSPF considers various factors such as network latency, bandwidth, and reliability when determining the best path. This makes it a dynamic and adaptable protocol, capable of responding to changes in network conditions. So to sum it all up, OSPF is a routing protocol that helps data packets find the most efficient path on the internet. It's open, adaptable, and versatile, making it a go-to choice for network engineers around the globe. Stay tuned to learn more about this fascinating protocol. Now, we dive into the intricate workings of OSPF. The Open Shortest Path First, or OSPF, is a fascinating protocol due to its unique method of operation. At its core, OSPF is a link state routing protocol, meaning it uses a complete picture of the network to calculate the shortest path for data transmission. Let's break down the step-by-step process of how OSPF works. When OSPF is activated on a router, it starts by discovering its directly connected neighbors. This discovery happens via hello packets, which the routers send out on their OSPF-enabled interfaces. When a router receives a hello packet from another router on the same network, a neighbor relationship is established. Once the neighbors are discovered, the routers exchange database description packets. These packets provide an overview of the router's link state database, which contains information about the network's topology. The next critical component is the link state advertisement, or LSA. Each router generates LSAs for the links it knows about and shares them with its neighbors. The LSA contains vital information about the state of the link, such as the link's cost, which is used by OSPF to calculate the shortest path. Once each router has received the LSAs from its neighbors, it can construct a complete map of the network topology. This map, known as the link state database, is identical on all OSPF routers within the same area. The final piece to the OSPF puzzle is the shortest path first algorithm. Using the information stored in the link state database, each router runs this algorithm to calculate the shortest path to each network. The result is a routing table that is optimized for the quickest possible data transmission. OSPF's operation might seem complex, but its efficiency in finding the shortest path is unmatched. From the initial neighbor discovery to the final routing table creation, every step in the OSPF process is designed to ensure data is routed in the most efficient way possible. So the next time you're marveling at the speed of your network, spare a thought for the humble OSPF protocol working diligently behind the scenes. What makes OSPF stand out from other routing protocols, you may ask? Well, let's delve into the unique features that make OSPF a dynamo in the world of routing protocols. Firstly, OSPF is known for its fast convergence. Convergence is the process of all routers agreeing on the network topology after a change has occurred. With OSPF, this process is speedy and efficient, thanks to the link state database that is replicated across all OSPF routers in a network. This means that all routers, have a complete and identical picture of the network, allowing for quick adjustments and minimal downtime. Secondly, there's scalability. OSPF is highly scalable, making it an ideal choice for large networks. It uses areas to subdivide networks, reducing the amount of routing information each router needs to hold and process. This subdivision not only enhances efficiency, but also reduces the amount of bandwidth used for routing updates. And then we have the OSPF's ability to choose the best path based on cost. Unlike other protocols that may rely solely on hop count, OSPF takes into account a variety of factors when determining the best path for data transmission. This cost calculation can include bandwidth, delay, reliability, and even administrative settings, making OSPF's path selection both flexible and optimized. Moreover, OSPF supports multiple equal cost paths to the same destination. This means that traffic can be shared across several paths, increasing the overall network performance and providing a level of redundancy. Finally, OSPF boasts an inbuilt security feature. It uses a process called authentication to verify the identity of routers sending OSPF messages. This ensures that only trusted devices can participate in the OSPF network, providing a layer of security against potential threats. In a nutshell, OSPF's fast convergence, scalability, cost-based path selection, support for multiple paths, and inbuilt security make it not just a routing protocol, but a powerhouse in network management. These features make OSPF a preferred choice for many network engineers. Wondering where OSPF finds its application? Let's explore. OSPF, or Open Shortest Path First, is a versatile routing protocol that finds its place in a variety of network environments. Its primary strength lies in its scalability, allowing it to be the go-to choice for larger network configurations. What makes OSPF a suitable choice for large networks? The answer is simple. Its ability to divide a network into different areas, making network management less of a headache. Imagine managing a city-wide network without any division or zoning. Sounds chaotic, right? That's where OSPF steps in. It allows network administrators to break down a large network into smaller, manageable areas. This way, the routing information is localized, reducing the load on the network and making it easier to troubleshoot issues. But OSPF doesn't just stop at large networks. It's equally useful in smaller setups as well. This is primarily due to its cost-based routing mechanism. In OSPF, the cost of a path is determined by the bandwidth of the link. So a higher bandwidth link has a lower cost, and OSPF will choose the path with the lowest total cost. This ensures that the most efficient routes are used for data transmission. Consider an office network where multiple routes exist between the server and the workstations. OSPF would automatically choose the path with the highest bandwidth and the least network congestion. This way, it ensures optimal use of network resources and a smoother data transmission experience. OSPF also finds its use in dynamic network environments where the network topology frequently changes. With its quick convergence time, OSPF can quickly adapt to network changes and update its routing table, ensuring uninterrupted data flow. In summary, whether it's a large network needing efficient management, a smaller network requiring cost-effective routing, or a dynamic network environment that demands quick adaptation, OSPF fits the bill. It's a testament to OSPF's flexibility and robustness that it finds application in such a wide range of scenarios. From small networks to large, OSPF proves its worth. How does OSPF fare when compared to other routing protocols? Well, let's take a look. When we compare OSPF with other protocols like RIP, which stands for Routing Information Protocol, and EIGRA-P, or Enhanced Interior Gateway Routing Protocol, OSPF stands out in several ways. First, let's talk about convergence. Convergence is the time it takes for a network to react to a change in topology, such as a router going offline. OSPF boasts faster convergence times than both RIP and EIGRA-P. This is largely due to OSPF's use of a link state database, which enables it to keep a complete topology map of the network. This means OSPF can quickly compute the shortest path to a destination, allowing for rapid adaptation to network changes. Next, let's discuss scalability. Scalability is a routing protocol's ability to handle growth in a network's size and complexity. OSPF shines in this department as well. It uses a hierarchical network design and areas to limit the scope of routing updates, which greatly reduces the amount of routing information each router needs to maintain. This makes OSPF highly scalable and well-suited for large networks, unlike RIP, which is limited to small networks due to its maximum hop count of just 15. OSPF also beats eGRAP when it comes to vendor neutrality. While iGRAP is a Cisco proprietary protocol, which means it works best with Cisco hardware, OSPF is an open standard, which means it can be implemented on routers from various vendors. This flexibility is a significant advantage, especially for networks comprising devices from multiple manufacturers. Finally, OSPF's support for both IPv4 and IPv6 is another noteworthy feature. While RIP and eGRAP also support both, OSPF's implementation is more efficient, making it a more future-proof choice as the world moves towards IPv6. So, to sum it all up, OSPF, with its faster convergence, greater scalability, vendor neutrality, and efficient support for IPv4 and IPv6, certainly packs a punch. OSPF's robust features give it an edge over other protocols. Now that we've covered the basics, let's delve deeper into OSPF. Our exploration of OSPF would be incomplete without touching on the concept of OSPF areas. In simple terms, an area is a logical grouping of networks, routers, and links in an OSPF network. The brilliance of OSPF lies in its ability to divide a large network into smaller, more manageable pieces known as areas. This division aids in reducing routing traffic, minimizing the size of routing tables, and keeping our network performance optimized. In an OSPF network, we can have several types of areas, including the backbone area, stub area, and not-so-stubby area, each with its unique properties and roles. The backbone area, for instance, serves as the hub for interconnecting all other OSPF areas. Moving on, let's talk about OSPF states. These states define the lifecycle of an OSPF router from the moment it starts until it forms an adjacency with another router. There are 7 OSPF states, starting from down state, where no information is exchanged, to full state, where routers have complete information about the network and can exchange routing updates. The transition from one state to another is not arbitrary. It's a carefully orchestrated process that involves several OSPF packets like hello packets, database description packets, link state request packets, link state update packets, and link state acknowledgement packets. Lastly, we have OSPF types. Not all routers in an OSPF network are the same. Depending on their role and placement, we have different types of OSPF routers like internal routers, area border routers, and autonomous system boundary routers. Each router type has specific responsibilities and functionalities within the OSPF network. In summary, OSPF's strength lies in its structure. Its ability to compartmentalize a network into areas, maintain a life cycle of states, and assign different roles to routers makes it a robust and efficient routing protocol. The more you understand OSPF, the more you'll appreciate its design and efficiency. We've learned a lot about OSPF today. Let's quickly recap. Today, we journeyed through the intricate world of OSPF, or Open Shortest Path First, a remarkable routing protocol that has become an essential tool in the network engineer's toolkit. We started with the basics, understanding that OSPF is a link state protocol, which means that it has a full topological map of the entire network. This allows OSPF to make more informed decisions about the best path for data to travel. We then delved into the workings of OSPF. We got into the nitty-gritty of how OSPF routers use a process called flooding to share information about network topology changes. This ensures that each router has a consistent, up-to-date map of the network, enabling it to calculate the shortest path to its destination. From there, we moved on to OSPF's unique features. We discovered how OSPF offers a hierarchical network design, which can reduce routing overhead. We also explored its ability to support multiple, equal-cost paths, allowing for load balancing of network traffic. Our exploration continued as we discussed various use cases of OSPF, highlighting its versatility. We saw how OSPF is often employed in large enterprise networks thanks to its scalability. Moreover, we understood how its fast convergence and loop-free paths make it an ideal choice for service provider networks as well. As we compared OSPF with other routing protocols, we realized how it stands out. Its ability to perform equal-cost multipath routing, its scalability, and its fast convergence time are just a few advantages that make OSPF a preferred choice over protocols like RIP or eGRP. Finally, we took a deep dive, delving into the more complex aspects of OSPF. We explored concepts like OSPF areas, LSAs, and DR/BDR elections, further cementing our understanding of this powerful routing protocol. Remember, the shortest path to understanding OSPF is through curiosity and learning. Keep exploring.